take them downing, take them downing, take them down. As you look, the whole room explodes. Take them downing, take them downing, take them. As you look, the whole room explodes.
Hi, I know it's a long day. I'll try to wake you up with a short story, about 30 minutes, about how we ended up building, and basically why we built a query engine on top of HBase, and afterwards HDFS, which is in some aspects better than Facebook Presto. My name is Asaf, and I work at Akamai. And to start the story, first, let's understand what is Akamai doing. Akamai is a CDN company. What is a CDN company? It's a content delivery network. Its customers are highly trafficked internet websites or your iPhone application or an Android application. Let's say, for example, Apple.com. On the left side, we have a web user trying to surf to Apple.com. Let's say that is based in Israel, and Apple.com server is based in the United States. He's surfing all the way to the United States and then back. This is the case that Apple.com is not a CDN customer. Let's say, for instance, that Apple.com is a CDN customer, an Akamai customer. Akamai has a network of servers deployed virtually in every major ISP. Like in Israel, we have servers deployed in the Internet Zahav and NetVision. When a web user is surfing to Apple.com, is basically surfing through the network of servers. First, approaching the server that is located very close to him. For example, in Israel, that would be in Petah Tikva, in Internet Zahav. Then goes all the way through the network of servers, approaching Apple.com. This gives the page two things. Akamai gives two things, acceleration and security. Acceleration means the page loads faster. Why it's faster? For instance, caching. We cache all the static content, and we retrieve them for the server that is close to the user. In our case, in Israel, for the server that is close in Israel. And the second thing is accelerating TCP traffic. Now I understand why everybody is standing here, because it's very... So the second thing is we accelerate the TCP traffic. Why? Because all the traffic goes through our network of servers, and we have special technology for accelerating TCP traffic. So in the end, what you get, if you're a Akamai customer, you get your page loads faster. That's acceleration. The second thing that Akamai gives you is security. Why? Since if you are a CDN customer, all your traffic must go and is going through the Akamai network of servers, meaning you have a point that you can detect a hacker or malicious request, because all the traffic goes through those network of servers. So for instance, on each such server, on each Akamai server, we have a web firewall deployed. So we can detect if a request is a malicious request, and if we detect it, we send an event to our security analytics center. In this event, we basically describe all the thing that is identifying the malicious request. Now, our story begins about 2 years ago. I worked at a startup called Cotendo. We were a very small player in the CDN market, and we were acquired by Akamai. And they gave us a mission. Our first mission was to design an analytics product for those events, because, well, the professional services person that we're using that needed to tune up the firewall needed some sort of analytics product to ask questions about those events. There are a lot of events sent there. So they told us, we want an analytics product. We said, OK. And then they said, but this is security. So we need it in real time. So this is a real-time analytics product we need. We said, OK. And then we asked, what's the size of all those events that are sent to the Security Analytics Center? And they said, oh, that's like 6 terabytes a day. So how much? 6 terabytes a day. We were overwhelmed. This is 42 terabytes a week and 180 terabytes per month. We did big data in Cotendo, but it wasn't that big. So we had a problem. So we sat and we started thinking how we're going to solve it. So first, we started thinking about what the product should look like. And we figured we want basically what Google Analytics gives you for the firewall events. So how does a product like this look? Let's say that the first thing that a professional services want to do is know how many events I have per day for a specific customer, of course. Then he selects a specific day, let's say 15th of March, and then he clicks, and now wants to see the events per host, per rule. He selects a specific firewall rule, let's say SQL injection, and then selects again, it's filtered by the day, the rule that I selected, and now I can see the events per host. And again, I can drill down and select a specific host and see all the events per path. So this gives the professional services person what he needs to understand how to tune the firewall. So this is what we wanted to build, a Google Analytics for the firewall events. But we have 2 requirements that we set out to build, were very important to us. One is response time. We wanted, when the user clicks, the response to be 1 to 2 or 3 second stop, like a sub-second query. The only problem with that, I remind you, we're supposed to receive 6 terabytes a day. This is raw data, and we also need to aggregate it. So that's one requirement. The second, we relaxed ourselves. We said, OK, we won't give you the ability to drill on all the dimensions, all the combination of dimensions possible. We're going to limit ourselves to predefined drills. So let's take a look at the product architecture. Why? To understand why we even needed to build a query engine. So it's fairly simple. We have more than 100,000 servers deployed all over the world, sending us security events to a receiver, some sort of a log receiver. It receives the events, sends it to a real-time aggregation engine, chunks it, aggregates it to the predefined data that we need, and saves it to a database. We chose Apache HBase. I'll soon talk about it. Why? On the other hand, we have the professional services person is using a UI. The UI has a front end, and the front end submits queries to retrieve the pre-aggregated data. We pre-aggregated it because we wanted the query to be fast. We want the query to be a sub-second query. So the UI obviously submits a query. Where? To HBase. The only problem with that is HBase doesn't support SQL. It doesn't. The only query the API gives you is fairly simple. You can define a primary key, and then you can say in the primary key, I want all the rows that are from ID 10 to ID 100 for that sake. Well, that's a problem. We can't really work with that, so we need some way to query the database in the way that we know, some sort of an SQL language. So what do we do? Start the Googling. Sorry? So the first thing that we saw was Apache MapReduce. So Apache MapReduce gives you the ability, Apache MapReduce is a specific implementation, but as a general sense, a general paradigm, it gives you the ability to write any code you want and run it on a lot of servers. Apache HBase, I didn't say it before, Apache HBase is a distributed database. meaning it's running on more than, the data is not located in one server, it's located on, let's say, 100 servers. So Apache MapReduce gives you the ability to write two pieces of code. One piece of code is running on the HBase node, on each HBase node, and doing something that you wrote, your own code. Basically, essentially, your query. You write it in code. The code is running, generating some sort of a response or a data, and then you can write a second piece of code. That second piece of code is running on a different set of machines, and this piece of code simply merges all the data together that was generated on each node, and then produces one single result. Well, it sounds great, but the only problem with that it's slow. It's very slow. Slow as in 10 to sometimes 30 seconds for a query that you write in code. Why? Why is it slow? Essentially, three main reasons. One, each time the query, the MapReduce runs your piece of code on an HBase nodes, it forks a process. It starts a process, a JVM process, in that matter. That takes time. 1, 2, 3 seconds sometimes. Second, when your piece of code finished producing the data on each HBase node, the data is written to disk, always. It's always written to disk, meaning latency. And the third thing is your second piece of code that is merging all the data from all the nodes. It doesn't start doing the process, running it, until all the data has been copied from all the nodes that is needed. Meaning it starts when the slowest one finishes. So we knew at that point in time, when we Googled it, that this won't suffice. We want a sub-second query, and Apache MapReduce won't give it. So we continued Googling. Apache MapReduce, that doesn't cut it. Next, we saw Cascading and Pig. So Cascading and Pig gives you a higher level language over Apache MapReduce. Instead of writing your code in Java, you can write it in those languages. You write less code. The only problem with that, it's slow. It's still running on MapReduce behind the scenes. So, it's not good. We continued searching. Hive. Hive sounds great. I mean, Hive gives you SQL over HBase or HDFS for that matter. There was only one problem with Hive. Hive, how does Hive work? It takes your SQL query, converts it into a logical plan, and then converts it into a physical plan. And that physical plan, each node is a MapReduce job. So essentially, we're still using MapReduce, so it's still slow. So we are at May 2012, roughly 2 years ago, and we were left with no other option than do it yourself. So we did. So before we begin, first we wrote the requirements. What do we need? Because this is a major accomplishment, writing a query engine on top of HBase or HDFS. And we didn't have a lot of time. We have roughly 8 months. So the first thing that we needed, we wanted the SQLite, select, from, where, group by, order by, and that's it. This is the first requirement, SQLite. Second, HBase as the source. We are not supporting, we want to retrieve from HBase, but only from HBase, not from HDFS or from any other sources, just focusing on HBase. Third, no joins in version 1. We only support one table in the from clause. And the last is to be flexible. When you write a MapReduce code, it's code, right? You can write anything with it. So you're not restricted to what SQL or ANSI SQL is restricting you. So we wanted the ability to say, we can't really anticipate anything that we would need. So we want the ability to say, okay, we want SQL, but we also want to inject our code in the middle of the phases. So those were the requirements that we wrote to ourselves that we wanted to make. So we made it. We called it Yoda. Let's take a look at a query example of Yoda. The query language that we chose was XML. And this XML is composed of 3 major parts. The first is query, then distribute, and then join. So query, essentially you write where you want, what and where you want to retrieve the data from in HBase. You write the HBase table name, you write the columns that you want to retrieve, and your filter using the where. Next, you write the distribute section. So the distribute section is very similar to the MapReduce code that you wrote, and run in the HBase node. But instead of writing in the Java, you write it in XML. We composed and wrote all the major, all the popular things that we would need. Group by, select, aggregate, top, order by. That's distribute. The last element is join. Join is not SQL join. It's simply an alias for merge. It simply means this is the second piece of code that merges all your data that was produced in the distribute section. This is like the second phase of MapReduce. Merges all the data together from all the nodes to create one unified result. So that's the query example. Now, let's take a look underneath. How does it really work? So first, let's understand what we're seeing in the diagram. On the bottom, you can see the HBase nodes. Let's say that we have 100 nodes, but we need to retrieve only from 10. So the first step, we submit the query to a Yoda. Which Yoda? We have, on each HBase node, we have a Yoda process running on each HBase node. When we submit the query, we arbitrarily pick one. So we have 100 HBase nodes, we have 100 Yodas, we pick one, and this one, we're calling it Yoda frontend. And the job of the Yoda frontend is essentially to parse the query and create some sort of a query plan. This query plan is composed of the query itself and a read plan. We go to HBase, we try to understand which of the servers we need to go to. So we have 100 HBase nodes, we need to go to 10 of them. We create a read plan for each HBase node. On the second phase, we send the query XML and its personal read plan to the Yoda waiting on a specific HBase node that has the data that we need. Yoda retrieves it, Yoda gets it, runs, executes the distribute section that you wrote on the query XML, fetches the data, runs the distribute section, and step 4 sends the partial query results back to the Yoda frontend, and then merges together all the data that was received from all the nodes and sends it back to the who called it in binary format. So that's the Yoda architecture at a glance. Let's try now to understand exactly what's the difference between Yoda, which is a query engine, and MapReduce. First, it's always on. When you run a MapReduce code, when it's MapReduce running your code on the HBase node, it needs to start a JVM process. In our case, Yoda is always running. So there's no wait time to start the JVM process. It's always there. Second is streaming. When you write, when HBase MapReduce, when Apache MapReduce runs your code on the HBase nodes, it always writes the result to disk. That's latency. And then it needs to copy the file, the results file, to the second node that will merge the data, right? So in our case, we don't. We simply, as soon as the record is ready to be sent, it is sent over the network to the other front end on the top. Meaning we're not writing to disk, and we're not waiting. In MapReduce, the second part of your code that merges the data waits for all the data to be shipped to it, and then starts the processing. We're not. As soon as the data is sent, as soon as the record is sent from one server, the processing starts. So there's no latency in that matter. Next is, just a second. Next, we wrote a specific, HBase has a specific problem. What is that problem? When you save a record, like let's take Hive for example. Hive, when it saves a record in HBase, it stores each column in your record, for that matter, in a HBase column. HBase, when the column is persisted to disk, it always concatenates the primary key to the column. So eventually, if you have a record that has 100 columns, you basically save the row key, your primary key for that record, 100 times. So that's not very storage efficient. So we knew that we were going to handle 6 terabytes of data per day, so we knew we needed to be storage efficient. So we devised a new way of saving the data to HBase, which means what we did, we essentially took the HBase record and serialized it and save it to one column as a binary. Enabled to actually read and parse the data and filter it, we needed to write code that runs inside HBase. And you can do that using HBase coprocessors. HBase coprocessor is essentially a stored procedure in HBase. You can write your code, a Java code, and that's what we did. We wrote a coprocessor that enables us to filter the data in HBase, in the HBase parsers, and also take only the columns that we need. So we don't ship all the columns. That essentially that enables us to be more storage efficient. So if we try to summarize the main differences between a query engine, Yoda for that matter, and HBase MapReduce, again, so HBase, the Hadoop ecosystem spawns the JVM process to run your code on HBase node. We don't. We have a daemon process. One thing that I haven't mentioned is auto-generated code. If you take Hive, for example, when Hive runs your data, it needs to represent a record in some way. That way, if you look at the code, it's using a hash map for representing your record. So essentially, each time a column needs to be retrieved during the process it runs the query, it's using fetch from the hash map. This is not very efficient. So in able to solve that, what we did, and it also made our code easier, is use the code generation pattern, design pattern. We simply took the query XML and simply generated Java code that will be executed and will be essentially the code that runs the query. So instead of having a hash map for the record, we have a class and an instance for each record, meaning direct access using fields. So that's auto-generated code that Yoda has. And as we said, the reducer, the second piece of code that merges your data, is waiting for all the data to be shipped. We are not. We are simply, immediately as the record is received at the Yoda frontend, the process starts. It starts processing. And the disk-based latency, we're not using disk. We're immediately sending it over the network. OK. So that was the differences between Yoda and MapReduce. So 2 years have passed. And we're always monitoring how the ecosystem has evolved. When we started, as I said before, we had no option of doing queries or any query engine over HBase. And apparently, after 2 years, we have. Essentially, every major open source company that is doing big data has developed its own version for a query engine, as you can see in the slide. When I started the presentation, I said that Yoda is better. We had to develop a query engine, which is in some aspects better than Facebook Presto. This is just an example. Why? if you take a look and read all the documentation for all those services, all the query engines, we couldn't find the set of requirements that we had in a single query engine. I mean, each query engine had one feature that we need, another feature that we needed, but not in a single product. What are those features? Let's just take a look at those three. First, be able to be flexible. Be able to inject your code. Facebook Presto only supports ANSI SQL. Hive QL. And of course, there are so many more query engines, but let's take just SQL. It's very restrictive. You can't really express any type of query or data processing for that matter in just a single SQL. It's very restrictive. Second is nested data type support. Let's take a record. A record is built from an int, a long, another long, and we had a different data type. We needed to have an array of record types. In the firewall, for example, when a malicious request is detected, the event that is sent is containing an array of rules that were triggered. So we want to save it inside on using an array of record types as a column. And this is something that Facebook Presto doesn't give you. It gives you very limited data types. You know, the primitive data types. But we needed that. And the third is efficient storage on HBase, which is, in our case, backed by coprocessors. So we needed a way to efficiently store the data on HBase, because as I said before, the data is saved not very efficiently in Facebook Presto. Why? Presto is using Hive if you want to store the data. And as I said before, Hive is not very efficient. And the last part, that our requirement, we wanted to have in HBase, your key is just a byte array. So Hive, for that matter, gives you only the ability to specify one column as your primary key. We wanted a compound column for our specific use case. And this is something that we had to develop because, again, Facebook Presto uses Hive, and Hive doesn't have it. So these are the features. So that's it. If you're into big data, we're hiring. We are now receiving 12 terabytes and expected to reach 30 by the end of the year per day. Thank you.